What we want to do in the course of this PowerPoint is we really want to be able to identify electrical symbols. You want to have some various electrical terms, and by the way, you guys already know those electrical terms, so we're not going to spend a lot of time on them. And we want to recognize the different types of electrical drawings that are out there. Okay, this is just an example of what electricians use when we're looking at schematics. Electrician schematics look a little bit different than ours. They're more of the pictorial type rather than the ladder type, because they're all about wiring and wire size and how things are connected to the equipment. We're more concerned about how things are working within the equipment. So again, there are two slightly different types of schematics. Okay, there's a lot of times where electricians will look at our schematics and scratch their heads, where we'll look at an electrician schematic and really not totally get it, and that's fine. I mean, honestly, I look at an electrician schematic and I sometimes have problems with it. I have a couple master electricians who I have to call occasionally. So recognize the different types of drawings. So there's two different types of electrical prints, and there's a pretty big difference between the two. We have residential prints, where electrical outlet switches are just drawn on the floor plan. Wire routing is determined by electrical contractor and electrical codes. In other words, there isn't a lot of detail on how you're going to run the wires or how the electricians are going to run the wires on the plans, because that's a lot of times left up to the contractor and the local building officials. Commercial prints are much more detailed in how electrical supplies are run. Okay, it tells you exactly where in the ceiling, where in the attic, or where above those ceilings electrical has to be run. It's detailed electrical diagrams prepared mostly by electrical engineers. The contractor does not have much of a say in any commercial prints. Where residential is, the contractor does have a lot of say in how things are run. Okay, electrical terminology, you guys all know this already. We have amps, voltage, watts, and a circuit. Okay, circuit has to be a complete circuit or things don't work. So I'm not going to spend a lot of time on this, okay? This is sometimes put into books for people that haven't had basic electrical, which you guys have all had. Okay, the circuit breaker is extremely important. Every circuit has to have a circuit breaker on it. There's always a breaker panel someplace on these prints. And it's important to double check when you're installing equipment to make sure that the circuit breaker is adequate to handle the equipment. About sometime in August, I walked into a restaurant. I was doing some insurance work, and I walked into a restaurant. I was up in New Jersey, up on the shore in New Jersey. And this restaurant was having air conditioning problems. The air conditioning just would not keep running, so they were filing an insurance claim. Something about lightning damage or something like that. I walked down into the basement, and they had a chair sitting in front of the breaker panel with a fan blowing air across the breaker panel. Okay, I'll probably post some pictures of that because this is a perfect example. Okay, the breaker panel was so hot when I touched it, it could have almost burned me. Okay, and that's how they were running their air conditioning. It appears that somebody put a new air conditioning system on the roof like 4 years prior, and the breaker panel was not sized properly for that equipment. So for 4 years, they had a chair sitting in front of their breaker panel blowing air across the panel. So that's just an example of why we need to make sure our breaker panels and our breakers are the correct size. In commercial building, we use a lot of conduit. Conduit is just a metal piping. It's usually aluminum, okay, sometimes steel or a mix, and its conductors are running inside of it. It uses stranded plain wire, runs inside of a conduit. You don't see that very often in residential construction, okay, unless it's the wiring is going outside. You see that more in commercial construction. A convenience receptacle is another name for an outlet. Okay, I don't know why they insist on calling convenience receptacle, but it's an outlet. Plug something into it. Service entrance is very important to find on your blueprints. Okay, even when you're installing HVAC systems, you have to find the service entrance if the building is just being built. The service entrance is where we bring the power in from the outside into the breaker panel or distribution panel. The reason we need to find that is you're not allowed to put any equipment within 36 inches of a service panel, okay, or service entrance. You have to have a clearance area there. The second reason you want to find it is because if it's coming in underground and you set a condenser over the wires coming in underground and maybe the wires aren't there yet, someone's going to take a backhoe and move your condenser to dig the hole. So we got to find out where the service entrance is. It's pretty important. The distribution panel, that's basically the breaker panel. It's the main breaker panel. Ground wires. Ground wires are also important. This is why we have to understand electrical prints. You've got to find the ground. Okay, the ground wires are 9 out of 10 times there's going to be a stake or a series of stakes in the ground outside the building where you have a ground wire connecting into your breaker panel to those stakes. Sometimes in older construction in the northeast part of the country, if you have copper water piping, it's going to connect to the copper water piping. Now that only works properly if the water piping coming in from the street is copper. It doesn't work properly if the water piping in the house is copper and that copper doesn't touch ground any place. I've seen that happen. Somebody had PVC water piping coming in from the street and it changed to copper once it came through the meter. Well, that does no good because there's no ground connection. Okay, so again, ground is very important to find. We don't want to set anything over. We don't want to install any equipment over the ground. Now, the Energy Star program was developed by the EPA and the Department of Energy. Okay, every product that's being released that is Energy Star compliant is rated for energy efficiency. The original objective was that it saves owners money and supposedly helps reduce greenhouse gas emissions. Now, the Energy Star program has continued to move on over time. It was started way back when. And now they're rating things like roofs, siding, and other stuff is all being rated for Energy Star compliant. It only is appropriate, and this is, again, comes into the installation thing. Your appliance or your air conditioning system is only Energy Star compliant if it's properly sized. In other words, it meets the specifications of the house or building, and it is properly installed. Okay, those are the key. If it's not properly sized or properly installed, it does not meet Energy Star compliance. So again, be careful about that. So this slide has a whole bunch of electrical symbols on it, and I'll make the big slides available online. I have the handouts available, but I'll make the full-size slides available probably tomorrow, and there's a reason for that. But this is the electrical symbols. Okay, you can find things like ceiling outlets, drop cords, bells, push buttons. These are electricians' schematic symbols. Okay, much different from the schematic symbols we use. Circuit breakers, fuse switches, okay, are all over here. That's probably the only symbol that actually makes sense is the switch. It's a $sign. Okay, they'd use an S basically is what it's called. But these are the schematic symbols that are used by electricians on their schematics. Any questions on so far, anything that I went over? Okay, when we look at a site plan, this is an electrical site plan. Okay, now this is a top view. Remember, site plan is not just the building, it's the property behind it. Anytime you see on an electrical plan where there's a long line, a short line, and I'm looking at the top left-hand corner of this. Let me get a pen. Looking at the top left corner of this. So I have a line coming here. Okay, it's dotted it's dashed, and it goes like the perimeter. That tells you it's buried electrical cable. You have some up here on the front of the building as well. You have some that runs across the parking lot here. Okay, and you have some that are here. Okay, that's buried electrical cable. And they get very upset when you dig a trench for like water piping or geothermal or something and cut across their buried electrical cable. Don't do it. So it might not be there when you're doing your installation, but it's very important to know if you're doing any outside work where those buried electrical cables are. Okay, so that's a site plan. Buried cable is always a long line, a dash, another long line, a dash, another long line, and it just keeps going on. This is our parking lot lights, is what these are. A residential electrical plan, I went over this a little bit yesterday, and I'm going to show you a larger version of a print so we can follow this through. But a residential electrical line, okay, if you take a look right where I've circled, there's $2 signs there. It's tough to see sometimes on a smaller screen, and again, I'm going to show you a larger print. $2 signs there. One's a switch, okay, and the other's a switch. But if you follow the wires, one is controlling our outdoor light right there. One's controlling the outdoor light right there. These are two carriage lights on either side of the garage door. So you have one switch controlling that. Then you have another switch that's controlling the lights inside my garage. Okay, so we know that that switch does the outside, that switch does the inside. Okay, so you can follow where the switches are in these electrical plans. Okay, now what this one does not appear to be showing is where the outlets are. Okay, so again, a residential electrical plant. Now, do they have to run the wire exactly in this pattern? No. They can run if they wanted to run the wire across this way and down there, they can do that. It's a residential plan. The electrician has a lot of say in how they run the wire. Most electricians will come up out of the breaker panel and run all the wire down the center of the house and basically break off that where they need to go. So there's a big spool of wire someplace in the center of the house. Commercial lighting plans, much more complicated. Okay, what you're looking at, all these little grids, like right there. Okay, there's a grid pattern. That's your suspended ceiling. So they're basically saying they're going to have a light fixture installed every other ceiling tile. Okay, fortunately, you don't have to be the one wiring this. The only reason you want to know that there's where the lights are is you need to know where you're going to put your supply and return ducts. Okay, because you can't put your supply duct straight across all the lights that are coming across the ceiling. Okay, so commercial electrical plans basically just tell you where the light fixtures are. Questions on this or the residential? Okay. Ground fault circuit interrupters, GFCIs. I don't know if they ever got that completely wired in the hallway and got those outlets installed where we were putting those basic electrical boards. But they're supposed to be putting a ground fault circuit in there. We will always install ground fault circuits where moisture may be present. Okay, bathrooms, kitchen countertops, garages, exterior receptacles, anything where you can come across moisture. We also use them in any situation in a commercial building where I'm concerned and I need basically an extra breaker. Okay, for example, in the hallway outside where we're installing all those boards, the basic electrical boards in the hallway by the classroom and the shop, okay, I wanted them to use ground fault circuit interrupt outlets there because it trips much faster and much more quickly if there's a fault in the circuit. Okay, so it's a little bit safer. So, but in bathrooms we use it because you could be standing in water and trying to plug something in with a bad cord. It will trip fast enough to prevent you from getting electrocuted. Kitchen countertop, same thing. I don't want water around electricity if there's a bad cord. Garages, because concrete, if you're standing on concrete and that concrete is damp and you touch something that has a charge on it or a bad extension cord or something, you can very easily get killed because concrete will conduct electricity if there's any moisture. Outside should be relatively self-explanatory. Grass is wet. We get rain. We have other things happening outside. You have an extension cord out there. The squirrel chews through the extension cord. Okay, and all of a sudden you have bare wires there. For some reason, the squirrels don't get zapped, but you will when you touch it. So you need to, outside circuits are supposed to be on ground fault interrupters. Now, in recent years, okay, the GFCI is not just in the outlet. Okay, we can actually put a GFCI breaker into the breaker panel. It does the same thing, but protects an entire circuit. So if I have 6 plugs in my kitchen on the counter, okay, I can protect the entire circuit with one GFCI breaker rather than putting in 6 different breakers or doing the daisy chain thing you can do off the outlets. Okay, it opens the circuit if you have a circuit imbalance basically of 0.006 amps. Okay, so again, if we think about line 1 and neutral, okay, we have a circuit with a light bulb here. And it's tough to draw with a mouse, so forgive me my bad drawings. Okay, but if I have 1 amp coming this way, and I only have 0.4 amps on that side, okay, so I have 1 amp on the line side and 0.4 amps on the neutral side. It means there's amperage going someplace. Okay, in other words, possibly a person touching it, probably maybe a ground, but this amperage is not the same between line and neutral. There's a circuit imbalance because we all know through a series circuit, the amperage should be the same. Okay, it senses that fault and it immediately turns off the power. And I mean, it's fast. Does anybody have any questions on the GFCIs? They're sort of important. Now, basements will have GFCI circuit breakers. So a lot of times condensate pumps, you know, the pumps that actually hang on the side of an air conditioning system or a furnace and pump the water out. Okay, condensation gets pumped out someplace. There's a lot of times condensate pumps are plugged into a GFCI outlet. Not the best idea in the entire world, but because it's a plug, because it's on a concrete floor, and because there's moisture around it, we sometimes plug those into an outlet. So the condensate pump might not be bad. It might just have had a trip on the GFCI breaker. It happens on occasion. You reset the GFCI and life goes on after you clean up the puddle of water. Arc fault interrupters, AFCIs, are more important these days. 2020 National Electrical Code basically insists that arc fault circuit interrupters be installed on just about every circuit in a building, especially residential. It is a different type of circuit breaker that actually detects if there's a spark in the system. Okay, again, arc fault interrupters detect if there's a spark or an arc in the circuit someplace. For example, if your Romix wire, which is the wire we use in a residential construction, if it's running through the attic and you have mice, and the mice start chewing through the insulation, they love insulation on wires for some reason, chipmunks like it too, but they start chewing through the insulation on the wire, and there's a slight spark. Okay, in other words, they get through the insulation and there's a slight spark. The arc fault circuit interrupter will shut off the power to that circuit. It will trip. Now, if you think it through, How do we have house fires that are caused by electrical? There's a slight spark that happens that ignites something else. So National Electrical Code and the NFPA, which is National Fire Protection Association, has changed the rules between 2017 and 2020. They started introducing it in 17, but it's gotten more specified in 20, that the majority of the circuits in your residential construction are going to have arc fault circuit interrupters. So if a breaker's popping, if one of these is popping for no good reason, it might not be the equipment. It might be the wiring that has gone bad. Personally, I did, as soon as these started coming out, I got almost a 15% insurance discount on my homeowner insurance by going and replacing all of my standard breakers with arc fault circuit interrupters. Okay, the insurance companies want these because it actually reduces house fires. So these will also work. Some of them have a GFCI combined in them, so you're getting both protections at the same time. But arc fault is very specifically looking at the arc. Okay, and I think it's probably one of the best improvements they made in circuit breakers in recent years. Electricians hate them, but I think they're really great. So the wiring diagram is used when wiring details cannot be clearly shown on a plan. It corresponds to a specific piece of equipment. Okay, in other words, if the big plan says the electrician is going to take wire to a junction box on the wall next to a boiler, after that junction box, it may have a square that points you to another diagram. Remember the sections and the littler diagrams that are used arrows in it? Okay, one of those might be a wiring diagram. Okay, it shows the different wiring used to connect specific pieces of equipment, especially larger equipment. So this is an example of a wiring diagram. Okay, we might have wiring coming to the right here, coming to the panel connections. Okay, 120 volts in neutral. Okay, this happens to be an exhaust fan. It's showing us that there's going to be a switch installed on the inside. Okay, and then the wire is going to run up to the roof, and it tells you the weight. There's a number 5 or 5 number 10 in a 3/4 inch galvanized rigid conduit. And then up on the roof, there's going to be a receptacle with a lid cover. And that's how the two fans, or the fan and the pump, install. Okay, so it's showing how the equipment is wired into the main, and it shows it in enough detail that an electrician can wire this. Because in most jurisdictions, you are only allowed to touch the equipment from where the power connects to the equipment or to the junction box, depending on the jurisdiction. Okay, you are not allowed to run the wire back to the switches or the breaker panel. That's the electrician's job. That's the standard. Now, some states allow differently, but most states, the electrician is responsible for getting it to the closest junction box on the piece of equipment. Does anybody have any questions on that? Okay, and if you ever work on a union job, don't touch any electrical. They get very upset. There's some electrical schedules. Okay, the most important one is the panel schedule. It lists the information associated with the distribution panel. You have a lighting schedule. It lists permanently mounted lighting fixtures. You have an equipment schedule. It details the wiring and the power information for every piece of equipment. Okay, I don't care about this one really as an HVAC technician. I care about the panel and I care about the equipment. The equipment, my equipment that's on that list has to match what's on the blueprint. So when I get equipment received on a job site, the first thing I'm going to do is take a copy of the blueprint and actually match it to the label on the equipment. If the amperage or voltage requirements are different, I have to identify that fast to whoever the electricians are or whoever the site manager is. So I always check the equipment schedule against what I receive. Panel schedule is very important because, again, the distribution panel has to have enough amperage available for us to be able to wire our equipment into it. Has to have enough amperage. This is an example of a panel schedule. Okay, this is a three-phase circuit. It tells you that in two places. You have 3P up there that tells it's a three-phase circuit, but you'll also see on the bus bars, these are the bars inside the electrical panel. It tells us phase A, B, and C. So it actually tells us what comes off of each circuit and each phase. For example, the first load, which is one of the lighting circuit in the gym, has a 20 amp breaker, and it comes off of phase A. Okay. You also have number 3, which is another gym lighting circuit. It comes off of phase B. They don't put everything off of one phase or the other phase because we want to do what we call balance the circuit out. Okay, now in some of these circuits, we're going to have a double pole breaker. For example, this is a double pole breaker that you would see on heavy circuits, such as, in this case, it's parking lights, but it might be on an air conditioning condenser or something like that. Basically, all it says is a double pole breaker. It's coming off 2 phases, okay, and it's basically pushing it together. Okay, it's a heavier breaker. They sometimes have little stars next to them that correspond with notes. Okay, basically it's like it's never going to get shut off. Night lights, they're always on, so they're locked on. The breaker will still trip, but there's a lock on it that you cannot manually turn this off unless it trips. So that's what's in a panel, and that's why, again, if there's an AC condenser that has a double pole breaker, that's your outside unit. If it's only rated for 20 amps and the condenser you need has a label on it that says 40 amps, you have to have a conversation with somebody because you can't install it on that circuit. It's not going to pass code and it's not going to work properly. Equipment schedule. The equipment schedule, again, is the one I'm most concerned about. Okay, I want to know, these are probably condensers. Each one of them runs at a maximum load of 27.9 amps. It's 230 volts, single phase. That's what the one is. Okay, and it's going to tell me exactly what the breakers are. Okay, it's a 40 amp breaker, 2 of them for each. Okay, it's going to tell me what the conduit size is, what the wire size is. Okay, this has to match what's on the label of the equipment, and it has to match what's in the installation manual. Okay, and sometimes you see a control diagram. Note, that just says there's a separate diagram for the controls, and that's what we showed you on that last diagram. That's the control diagram. Any questions on the equipment schedule? Because that's relatively important. Any questions on the equipment schedule? Okay. So again, there's another type of diagram. It's a one-line diagram. It's a type of schematic diagram, and it's also called a riser diagram. These are basically used for controls and for main circuits. Okay, for example, this is my circuit coming in from the street. We go through a utility transformer. That's the responsibility of the power company. And we come into a panel distribution. There might be additional, these are my air handlers up here. And all it does is give from the panel what has to be wired. There's sub-panels here. There's 3 sub-panels. But again, it's called a riser diagram. You don't have to worry too much about these, except to make sure that all of your air handlers and equipment has wiring. They're not shown all the time on every print, but if they're there, make sure they match what you're installing. Okay, an electrical circuit we've talked so much about. It's part of basic electrical. Okay, it's path of electricity from a source to a component and back. It's numbered on a drawing and connected with a heavy line. The arrow indicates the circuit is connected to a distribution panel. Larger conductors are used in feeder circuit to avoid voltage drops. Okay, we use the larger conductors. It just carries more electricity and prevents lights from dimming and stuff like that when equipment comes on. Branch circuits are general lighting circuits, appliance circuits, individual circuits, and sometimes we have dedicated circuits. All of our HVAC equipment will always be a dedicated circuit. We never put equipment on multiple pieces of equipment on a single breaker. Doesn't happen. Not legal. Okay, it's also used for computers and other specialized equipment that we don't want to have anything else taking a chance of popping that breaker. Circuit sizing, okay, we're not going to go into this because the calculations on how to properly size wire are not straightforward. As an HVAC technician, you're going to be looking in the install manual and on the labels of the equipment. That is what you use. Now, the electricians, they spend an entire course on load sizing and branch circuit calculations. Okay, it's not as straightforward as it seems it is. The length of the run from the breaker panel, the size of the equipment, the size of the wire, motor calculations all fall into this. Okay, but again, this is done by electricians and an engineer. You are responsible for the label on the pieces of the equipment matching what the engineers have come up with. So don't get crazy about circuit calculations. Low voltage systems, it allows for controlled switching. Okay, our biggest low voltage system we use in HVAC is the thermostats. Your thermostats is a low voltage system. Other examples could be a doorbell, and in some houses they use a low voltage control system that goes to, basically it's the push button light switches and stuff. Activates a relay. It's a much higher end electrical installation. Everything goes to the basement, and then there's a whole box of relays where you basically push a button and it activates a relay. Neat system, but very expensive to maintain. Okay, starting more and more frequently because of green building ideas, we have alternative energy sources. We reduce energy costs. We can recover installation costs over several years. Some of these might be wind powered. Okay, see a lot of that on the shore these days is the wind powered. Some systems allow them to sell the unused electricity back to the local utility company. More importantly, more and more, you're seeing solar systems on every house. Now, this affects you, okay, because solar installs do not do great with spikes of electricity. So you may get a call from a homeowner that says, could you please install, and they'll give you the name of like a capacitor or a hard start kit that their solar company wants them to install. All it does is basically takes out the starting amperage, that heavy start amperage on a compressor. Okay, the compressor may be a PSC compressor motor, has a permanent run capacitor in it. Okay, but they might want you to make it to a CSCR, which you're basically adding a hard start kit to it. You're adding a start capacitor and a relay. What that does, it lowers the starting amperage, and it's much more compatible with solar power. So just be aware if you have a solar panel, if you pull up to a house and there's solar panels, just be aware that there's two sources of power. Okay, if things are working right, if for some reason you have to shut off the main breaker to fix something, the solar energy should automatically disconnect, but always check it. Okay? It's very important because you could get zapped by the solar cells even though you have the power shut off. Electrical codes, not only are you responsible as an HVAC technician for following mechanical codes, anything you install must follow National Electrical Code. That's why we cover these plans. That's why we talk about this a bit. Because everything you install has to meet National Electrical Codes. Part of that is being UL listed. So any furnace, any air handler, anything you install, If you're buying it from overseas, or your customer decides to buy from eBay because something is too expensive and you go install it, make sure it has a UL listing. Now, part of National Electrical Code and part of International Mechanical Code says you will pull a permit. So make sure you pull permits for things you install. Okay, because again, once that inspection is done on a permit, the responsibility and the liability shifts from the installer or the installing contractor to the city or county, whoever was the permit was pulled through and did the inspection. So permits are very important. Conductors is normally copper wiring. We don't use aluminum wiring for branch circuits anymore. It might be used on your service feed. In other words, from the pole to the house or from the transformer on the road to the house. Okay, might be aluminum wiring, but we don't often use it anymore in interior branch circuits. Fires happened on that through the 1970s, and they stopped using aluminum wire inside the buildings, other than for service feed. Conductor size is designated by gauge numbers, and it's based on the diameter of a wire. As the wire number decreases, as the gauge decreases, the wire size increases. It's backwards. So a 10 gauge wire, or 10 AWG, is actually thicker than an 18 gauge wire. Okay, just to give you an example you've seen, thermostat wiring is 18 gauge. Okay, computer network wiring is 22 gauge. Okay, the wiring that we were using off the spools in the shop when we wire circuit boards is either 12 gauge or 14 gauge, whichever one you decided to grab. Okay, so as the wire number decreases, the wire size increases. It's completely backwards from what you would think. And I don't know who came up with that. Most residential wiring is 12 gauge. AWG, American Wire Gauge, copper wire. 14 gauge is the smallest conductor that is allowed to be used in line voltage branch circuits. Anything smaller than that has to be control voltage. The longer the run, the larger the wire size. It prevents voltage drops. Wire sizes larger than 4 AWG are specified in circular mills. Not worried about that right now because you're never going to touch it. It's measured a cross section. Okay, so again, the larger the wire size, the smaller the wire. 14 we use pretty heavily, 12 we use very heavily, 10 we use, and if you're installing electric heat someplace, you may come across 8 and 6, okay, for very heavy amperage circuits. If you're working commercial, on commercial chillers, and again, I'll try to find the picture I took of this, you might come across 2. Very, very heavy. I mean, you're talking here, you might have a 400 amp circuit. Okay, very heavy wiring. So, again, wire size, the lower the number, the larger the wire, the larger the amperage. Any questions on that one? That one's pretty important. Okay, conductor insulation is pretty important. You look at the roll of the wire you're using sometime. Okay, you look at it, THHN is normally what we use. Okay, this is what I normally order for the shops, THHN. Okay, it's flame retardant, it's heat resistance, it's a thermoplastic. Okay, if I'm ordering stuff for a condenser install, something that's going to be outside or in a moist area, I'm going to order THHW. The W stands for water. If I'm going to order something that's going to run through what we call a plenum, in other words, through an airstream, I'm going to order THWN. Okay, it's flame retardant. Okay, moisture and heat resistance. And you just, THW is just, again, flame retardant, moisture and heat resistant, and then you have UF, which is just moisture resistance. I've never seen that used, really. But again, the types of insulation makes a difference. That's going to be specified on the plans. Again, you don't have to worry about this most often because this is part of the electrician's job, but it doesn't hurt to always check. Conduits are rigid metal or electrical metal tubing or flexible metal conduits, okay, found most often in commercial environments, with one exception. Recent electrical code and recent mechanical code says that anything installed next to a boiler or a furnace has to be in a conduit. Okay, so you may see from the top, from like a ceiling in a basement down to the furnace or boiler, you may see a conduit. That's because it's required, because it's heat resistant. It prevents fire. And basically that is how we take a look at electrical plans. Now I do want to show you an electrical plan on a true schematic, okay? So I'm gonna switch over to here. Okay, when you look at your activity 15-1, okay, that's in your book. 15-1 has you looking at electrical plans for a residential building project. Okay, this just happens to be, there's 3 sets of prints that we're going to use: MAR02, MAR04, MAR06. They all have to do with the electrical plans. So the first question on 15-1 says, what amp service is provided to the main breaker panel? Where is the main breaker panel located? Okay, well, you have to look around for it, because someplace, usually in the basement, there's a main breaker panel. Okay, and sometimes it's not easy to find, so you actually have to look for it. Okay, in this case, we have a main breaker panel. It's designated on our plans, okay, and it's right over here. This is in the basement. MAR02 is basement. Okay, and if you look at the breaker panel designation on the right-hand side here, you'll see that our main breaker panel's on the right side of the basement. That's the right side of the house, and it says it's 200 amp service. So your answer for question 1 is 200 amp service, right side of basement. That's how you find, that's basically what we're going to be doing going through this print. It's just asking you to find the different stuff. Okay. Question number 2, it's looking for where the smoke detectors are located. Okay. Again, we're looking for where smoke detectors are located. So you're going to use the symbol sheets that are in your chapter. There's symbols, and you're going to find where the smoke detectors are. And in this case, you have to look closely at the plan, but there's an SD right there. Smoke detector when you look to the symbols, okay, and there's a note number 1, and I'll show you what that says, but that's your smoke detector. So the basement, which is question 2A, is near the basement stairs, and you're going to do the same thing on the prints 4 and 6. So all of this is just an identification of where things are on the prints. Okay, so if we skip over to 8, it says how many lights are in the following area. Okay, so I'm going to go to the first floor where the garage is, and I've shown you this plan already once. Okay, but 8B says how many lights are in the garage. Well, I have 1 right there, and I have 1 right there. Those are the only 2 lights in the garage. So it will be 2. Okay, in the master bathroom, how many lights do I have in the master bathroom? Okay, I have 1. I have 2. There appears to be 1 there in the shower, or whatever that is over there. And there's 1 over each of the sinks, if you look closely. Okay, so in the master bath, I have 5 lights. This is a ceiling fan right there. That's not a light. So that's what 15-1 is asking you to do, is just identify the different components. 15-2, you're doing the same thing with a commercial building. Okay, so that's what we're asking you to do in those. So give me one sec. Let me get rid of the recording here, and then